So this is how generally a tension test curve looks like. If we take stress versus strain, engineering stress versus engineering strain, this is a straight line and the slope is called Young's modulus. So what are the different parameters? Like true elastic limit, so what is this? This is basically identified by motion of very few dislocations, like 100 or 200 dislocations. So this can be measured by microstrain measurements. This is the one. Second one, just remember these terms because sometimes they ask what is the difference between this. One is their proportional limit. So this is this point, highest point, at which Hooke's law is valid. That means stress is directly proportional to strain. So what is elastic limit? This is the highest deformation any material can withstand. Without any measurable permanent deformation. These things we usually don't get in tension test, but this is for a reference only because sometimes in GATE they ask what is the difference between proportional limit and elastic limit, what is true elastic limit. So this is just we know that slip happens or deformation happens by motion of dislocations. So very few dislocations like 100 or 200 dislocations when they are moved, that is called true elastic limit. And the proportional limit is this point, highest point, exactly the point at which Hooke's law is valid. And elastic limit is the highest deformation any material can withstand without any measurable permanent deformation. Then the most important is yield strength. So what is this? This is the point where offset strain of 0.2%. This we usually take as yield strength of the material.
Sir, out of these three limits,
yes,
what would be that particular point where on if I release the load completely, my material will come back to its initial state?
That is this point, proportional limit. Because
Okay,
because here in elastic limit there is some permanent plastic deformation that we can't measure, but it is exactly the point at which stress is directly proportional to strain. So this is the highest point in the straight line. So if we release the load, this will exactly come to its original dimensions. Okay.
Yes, sir.
Now what are the parameters? First we take engineering strain, that is P by A0, load by initial cross section area. What is the engineering strain? Change in length by original length. So true strain, that is load by instantaneous area. And this value and true strain, that is ln L by L0. These two values we cannot directly measure from the tension test. You have to first get these values, then we convert them using this formula. Okay, so you first calculate these two. You get this from the tension test. Usually you get the load versus elongation. Okay, from there you measure the stress, that is load divided by area, and you get the elongation, so you calculate delta L by L. So this is E, load by area, this is engineering stress. So you get these two values and then you put here to get the true stress, true strain values. And the true stress, true strain, that curve, suppose this is something like this is engineering curve, engineering. So true stress, true strain curve will always remain like this, straight up to here, then after there will be some curvature, it will go something like this, always to the left and above the engineering curve. So many times GATE has asked these questions. So you know why this happens, like why engineering stress strain curve is always below the true stress strain curve? Because we are taking area constant. So once necking happens, because you know if necking happens, suppose here necking is happening in the sample, so the area will reduce, but we are taking the actual initial cross section area, that is this. So that's why it becomes low. But in true stress strain curve, what we take the instantaneous area always. That's why this remains above, always above and to the left. So one important factor is reduction in area. That is
explain why
because what is our engineering strain, that is P by A0. Okay, so A0 is the initial, suppose we have the sample, I'll draw here. So this is the cross section area, initially we take as A0. Okay, but when necking happens at the highest point, I will go to that, how necking happens and what is the condition for instability. Okay, so when necking happens at this region, it becomes thinner. So this area is less than A0. Okay, so our true stress is P by A always. This is the instantaneous area. So if area is less, what will happen to stress? It will go up because denominator is decreasing here.
Stress will increase.
That's why this goes up, always up, because we are dealing with instantaneous area here. So this reduction in area, what is this? A0 minus AF by A0. This AF is the cross section area at fracture. Okay, so this is basically a measure of ductility. So we can write it like A0 minus AF, so we can write 1 minus AF by A0. Okay, remember this reduction area is 1 minus AF by A0. Now what we can do, suppose you take 1 by 1 minus R. So what will be this? 1 by 1 minus AF by A0. Okay, so from 1 minus R we have derived this A0 is equal to A0 by AF, and we know area remains constant during plastic deformation, so AL constant. So that means A0 L0 equal to AF LF. That means A0 by AF to LF by L0. That's what I have written here. Okay, so this is what we can directly calculate strain, because strain we know true strain ln L by L0 or is equal to ln A0 by A. Okay, so if reduction in area is given, so what you can do, you can calculate directly strain by just putting ln 1 by 1 minus R. Okay. I will write it clearly. Okay, so it is given, suppose 50% reduction in area, R is given. So the question asked, calculate the true strain. So how to calculate? You can directly put ln 1 by 1 minus R. It will save your time, because 1 by 1 minus R we saw equal to A0 by AF. A0 by AF. So this is nothing but L F by L0. Okay, so true strain equal to ln LF by L0. So if this is given, you can directly calculate the true strain from this. You don't have to calculate A0, then AF, then go to all those things. Similarly, if you want to calculate the elastic, the engineering strain, what is this? L minus L0 by L0. We can write it as, what is this term we saw here? What is this? A0 by A or AF, whatever this is. 1 by 1 minus R we know from this relation. So this will become R by 1 minus R. Okay, if reduction in area is given, you can directly calculate engineering strain from this and true strain from this. Is it clear?
Yes, sir.
Okay, so now we'll go to what is resilience. I've told these things before, I think in this class. So now it is the ability to get back to original shape after elastic deformation. Okay, so suppose in the stress strain curve, you load the material to this point and then release the load, then what will happen? This will come back to its original shape. There will be no plastic deformation. So this property is called resilience. So this is half into yield stress, true yield stress into true strain at the yield point. So we know stress strain are linearly connected, so we can replace strain by sigma y by E. Then we get this relation. So one basic questions that get asked is, suppose for a spring material, what properties are required? We know that spring material, it has to come back to its original shape quickly. So what should be the properties? What should be the yield strength? What should be the elastic modulus? That is at a good resilience. We see here yield strength is directly proportional to this, so sigma y should be higher and elastic modulus, it is in denominator, so it should be lower. Okay, so ideal material for restoring energy load should have high yield strength and low elastic modulus. Okay. So now we'll consider true stress at maximum load. You know the relation, suppose engineering stress at maximum load, that is maximum load divided by original cross section area, and true strain at maximum load, this U is for ultimate tensile strength or compressive strength, whatever it is. Okay, ln initial cross section area by cross section area at the highest load. So we'll put this here. Okay, so here see P max, it implies that P max equal to ACU A0. Okay, so sigma U equal to P max by AU. So what is P max? This is ACU A0. So I put that thing here. Instead of P max, I put ACU A0 by AU. Okay, so we know strain is ln A0 by AU, true strain. So if we put exponential here, this ln, this will cancel out. So we'll get exponential strain equal to A0 by AU. So that's what here A0 by AU we have. So I've replaced this A0 by AU by exponential true strain at maximum load. So this is one important relation. Okay, see, you can calculate everything by manipulating the relations. So this is very important relation. You must remember this. So did you understand how I derived this? First you have ACU, that is elastic engineering stress at maximum load, P max by A0. Then what I do, P max is equal to ACU A0. So I put here this true stress at maximum load, that is P max by AU. This is the instantaneous load at maximum load. Okay, so I put here sigma equal to ACU A0 by AU. Then I just put exponential to delete this ln term. Just see it once. If you have any doubt, ask me. Though derivation is not important, still you should understand how these relations are coming.
Understood.
Okay. So another term is there, that is strain hardening exponent. Denoted by N. What is this? If we have a stress strain curve, we have to first convert, if it is given in engineering terms, we have to first convert it into true stress strain curve. Then we take ln stress versus ln strain. We plot this curve. This will be linear. Then the slope of this becomes n. Another term is there, that is strain rate sensitivity. How your deformation behavior changes with strain rate. Suppose we take 10 to the minus 2 per second strain rate or 10 to the minus 3 per second. So how the deformation behavior changes, that is denoted by strain rate sensitivity. How we calculate that? We just calculate ln from this curve. First we get this ln stress versus strain, true stress strain curve. Then we plot ln stress versus ln strain rate. So that slope is m, your strain rate sensitivity.
So ln E not what is
This one,
rate sensitivity? Yes, sir.
this is strain rate. You have to plot first stress versus strain rate curve. Then you put ln stress versus ln strain rate. Then you calculate the slope.
Okay, sir.
That is your m. Suppose this is a load versus elongation curve. So at this point, we know the derivative is 0. Okay, the slope is 0 here. So this is the maximum load point. So the condition is dp equal to 0 at that point. And we know that load equal to area into stress. So we know P equal to A sigma. So what is dP? We'll differentiate both A dP AD sigma plus sigma dA equal to 0 at maximum load. So this implies d sigma by sigma equal to minus dA by A. And we know from plastic the constancy of volume during plastic deformation. So AL equal to A0 L0. So if we differentiate this, so what do we get from these two relations? D sigma by sigma equal to dl by L. Okay, so what we get is d sigma by sigma equal to dl by L. What is dl by L? How we calculate true strain? The definition is
dl by L will be equal to E.
Not E, that will be D, the change in true strain. Because this is if dl by L, then if we integrate this from 0 to E equal to this, we integrate from L0 to L dl by L. So this will be d ln L with the limits L0 to L. So this will be ln L by L0. So this is the definition of true strain. This is how we get this relation. Okay, so first basic relation is this. From this we derive this main equation. So this dl by L will be dE. So what we get is d sigma by okay, from this what we derive d sigma by, we just consider these two, dE equal to sigma. Okay, so this is the important relation that is required for instability and tension. Okay, the slope of true stress, true strain curve should be equal to the true stress. So how do you show this graphically? True stress, true strain. So here we are considering only the plastic region. So I will just draw the plastic region here. This is our tensile curve going like this. Another curve will come. I will show it in different color. So this curve is stress strain curve, and this curve is d sigma by dE. Okay, so at this point they intersect. So at this point d sigma by dE equal to sigma. Okay, so what is this strain? This is the plastic strain up to the highest point. So if we plot the engineering stress strain curve, that will be something like this. It will go not straight, something like this. And this point will consider something like here to this point. Because as I said, the true stress curve is always to the left. So if we have some point in engineering strain here, that will be reflected in true stress strain curve here. If it is here, then it will go here like this. Okay, so this amount is the true stress up to the highest load. True strain. Okay, so important relation is this, you have to remember. D sigma by D equal to sigma. This is the condition for plastic instability, at which necking starts. At this point, what happens? The meaning of plastic instability itself is the beginning of necking, or beginning of necking. So how necking happens, if you see, we have a sample like this. I'll draw only the gauge section, forget about the rest. Okay, so we are loading in this direction. So what happened, this is not a single crystal, this is a polycrystalline material, so there will be grains. And at each grain, the orientation of the planes is different. Okay. This is one reason. Also, there could be some voids or defects. So when we load, what happens? In some grains, when they are oriented such that the critical resolved shear stress is low. Okay, so those will start deforming fast. Plastic deformation will start and they will deform. At certain location, they will start deforming. So after certain deformation, what happens? Strain hardening will occur at those regions. Okay, so first there is some deformation and then strain hardening occur and those deformation will stop. Then again another weak point will be found where maybe some void is there or some orientation is such that at certain high stress level, so those CRSs will be sufficient to activate slip. So in those grains slip will start. Again those, what happen? After certain deformation they will also strain harden. So this is how uniform deformation takes place, uniform elongation that we say up to the, so I hope you know that uniform deformation is valid only up to the maximum point or to the point where necking starts. In engineering stress strain curve up to the highest point, up to this point our uniform elongation is valid. Uniform elongation occurs up to this point. After that it is not valid, because there will be necking and all the deformation will be concentrated to one small region. Okay, so if I ask what is the limit to which uniform elongation occurs, it is up to the point of necking or to the maximum load. Okay, so this thing will happen, strain hardening at certain points, and then they will stop. Other regions will get weakened. There will be deformation and there will be again strain hardening up to the point where so plastic deformation will take place. Like I said, some weak regions will be there where there will be deformation and then strain hardening, then other weak regions plastic deformation will take place there and then there will be strain hardening there also. So what happens? As long as increase in load bearing capacity associated with strain hardening is greater than decrease in load bearing capacity due to decrease in cross section area. So two things are competing here. One is strain hardening versus decrease in cross section area. Okay, so this is what strengthens the material, increases the load bearing capacity, and this is what reduces this. So at the maximum point, Suppose here what happened, the rate of the strain hardening is equal to the rate at which the cross section area is reducing. So at this point, the load bearing capacity associated with strain hardening is equal to the decrease in load bearing capacity due to decrease in cross section. So after this, strain hardening will reduce and this will take over. Okay, so up to this region we get uniform elongation. After this is not valid. We use the relation stress equal to this relation is valid only in this region. Okay, only in this region this equation is valid. Plastic, this is elastic, so I don't consider this. This is only for plastic region up to the point where necking starts. Is it clear? Did you all get this point? What I'm explaining here?
Yes, sir.
This is one interesting phenomena we see usually in mild steels, medium carbon steels. So why this happens? This is related to the solute concentration. Okay, so we know if we have a dislocation, at here core of dislocation, suppose we like this line is going into the plane of this surface, there is a place where atoms can be accommodated, interstitial. Below this side we have tensile residual stress, and in this side we have compressive. Okay, so as here the place is big, just below the core of dislocation, this attracts solute atoms like carbon, nitrogen. So what happens? Suppose we have a dislocation line like this, H dislocation. So just below this, the atoms go and segregate. This is called pinning of dislocations. And we need a higher amount of stress to break this atmosphere. This is called Cottrell atmosphere. Okay, so this is why first the stress goes high up to the point. At this point, this Cottrell atmosphere is broken and the dislocation is free. So the stress releases.
Well, one thing is that, like you said, carbon and nitrogen causes this pinning of the dislocation. So,
Yeah.
like, is it that every small atom will cause this pinning, or this carbon and nitrogen are the only examples?
No, they usually do. Why I take carbon nitrogen? Because in steels, this is an example of steel, mild steel. So in that carbon and nitrogen are present. And these are interstitial atoms. Okay, small atoms. So probability is more that these will segregate. Otherwise, if you take hydrogen also, that can cause any atom that is small that can segregate to the core of dislocations.
Okay, sir. So means that the probability of finding hydrogen is less, but hydrogen has the capability to segregate.
Yes. Any atom. In fact, this phenomena is not observed only in steel. In other metals like I don't know, but nickel or something like that. Anywhere where there is solute atoms, and if there is interstitial atoms like small atoms like carbon, nitrogen are present, then they will segregate to the core of the dislocation.
Okay, sir. And sir, there is one question in the chat box that how vacancies affect the uniform allocation.
Okay. So if you have vacancies, so what happens during tension test? So they will coalesce. Okay. If vacancies are close together, they will coalesce and then they will form a void. So then what happens? That area will be weak region. So weak region means, suppose we have a sample and we have vacancies here and we are loading in this direction. Okay, so what will happen? They will coalesce and form a void. So what happened now in this region, area is A0. This region, the area is reduced. A is less than A0. So what will happen? Load will increase because we know stress equal to load by area. If area is small, the stress will be higher in this region. Okay, so this region will start deforming more. Vacancies here in the sense, we're not talking about the atomic vacancies. Maybe this is mainly the voids, like during fabrication of the material. If some defects are there, like voids, formation, porosity, these are there. So I'm talking about this. Usually vacancies can't affect much. So vacancy is not the right term, it should be voids. Any region where there is some defect, so there the same thing will happen. The regions will be weakened and deformation will take place in those regions. Then what happens? Then strain hardening will occur in those regions and that will stop. Some other region will be picked up. Okay, exactly I don't know vacancies how they will affect I don't think they will affect much. This is voids, not vacancies. Weak regions in the sample. That's what I mean, not vacancies. Vacancies won't affect much. Okay. So any more doubts? Okay, so this yield point phenomenon, this has many other things like upper yield point, lower yield point, how this Luder bands form. So this will take about 30 to 40 minutes to explain. So many things are going on inside. If you want to see details how these things, like if you want to read properly, we can watch. There is a video series of IIT Kanpur. Per gate, I don't think that much is required, but if you want, you can watch. Sudhanshu Shekhar Singh. Defects in crystalline solids. The course name is this, Defects in Crystalline Solids. All the dislocations, vacancies, this yield point phenomena, everything is explained properly there. You can watch. Okay, so today I'll stop here. See you next week. Okay. Strain rate sensitivity. Here. Is there any doubt here? I think so.